All right, welcome back, everyone. Our last talk of the afternoon. I'm speaking on Igusa stacks and local global compatibility.
Thanks for the invitation, and thanks everyone for coming. So the local global compatibility in this talk, in the title of this talk, refers to the compatibility of constructions in local and global Langlands correspondences. And everything I want to say today is based on the joint work with Patrick Daniels, Paul van Hoften, Daniel Kim, and separately a joint work with Ana Caraiani. So to put everything into context, let's recall the global Langlands correspondence or conjectures. So we start with a connected reductive group over a global field, which will be some number field for us. And even in this talk, I'll mostly just use the case where f is the rational numbers. And we fix an isomorphism between QR bar with the complex numbers where L is some rational prime. And then a version of the global Langlands conjecture made precise by Bazard and G says that for any automorphic representation of the adelic points of G with a suitable algebraicity condition, so which they call L algebraic or C algebraic, one can attach a Langlands parameter to it, and which will be a continuous Galois representation of the absolute Galois group of F into a suitable notion of a dual group of G. So I should write for G. And which will be the L group or C group according to the algebraicity condition you put. But the definition of these are not very relevant to us. So there will be, and this attachment should satisfy certain conditions. And in particular, they should be compatible with the construction of local Langlands correspondences. When you restrict to any place of F. So I will write LLC as an abbreviation for local Langlands correspondence. So as an example, how such a global Langlands correspondence can be constructed for certain type of automorphic representations, and also to give you a sense what it concretely means to be compatible with local Langlands correspondence, let's look at the case where G is GL2 over the rational numbers, and then I'll consider some compact open subgroup of the finite adelic points of G. So then we'll look at the modular curve at the corresponding level with its universal elliptic curve over it. And then for any integer k greater or equal to 2, we can look at the local system on this modular curve obtained by taking symmetric k minus 2 power of the first Étale cohomology of this relative Étale cohomology of this universal elliptic curve with QR bar coefficients. And then we can maybe this, okay, look at the colimit of the cohomology of the modular curve with coefficient in these local systems And what people usually call this parabolic cohomology, this is the image of the compact support cohomology in the usual cohomology. We take co-limit over all finite levels to get a cohomology. This will be a representation of the product group of the finite adelic points of G with the absolute Galois group of Q. Then theorem due to many people, originally Aichler Shimura. Then Deline, Igusa, perhaps Langlands, and then completed by Caraiani and Saito, is that, so this cohomology as a representation of this product group decomposes into the direct sum over all cusp new forms of of weight K into a box product, box tensor of the finite part of an automorphic representation generated by this cusp form. With a Galois representation attached to this modular form. And then moreover, one can recover this finite part of the automorphic representation by taking the restricted product of an explicitly constructed local Langlands correspondence attached to the restriction of this Galois representation to the corresponding decomposition group. And then this Galois representation should be almost everywhere unramified. And is characterized by Aichler-Shimura relations at all unramified places. So which says that the Frobenius characteristic polynomial should have a specific form, and these are the Hecke polynomials. So in this example, we have seen that for this specific group, one can construct like a conjectural attachment to automorphic representations of this form by simply assign to it a Galois representation that appears in this decomposition of the cohomology group. But generally, there are no such clean relations for general groups. So therefore, before we even talk about the local global compatibilities, we have to ask ourselves what are the available constructions of a local or global Langlands correspondences. So in the local Langlands correspondences, recently the work of Fargues Scholze gave a rather pleasant answer, or a uniform construction, at least of semi-simple L parameters that works in great generality. Well, for the global Langlands correspondence, as I have said, there are no such clear picture, but almost all known results of constructing Galois representations come from studying the cohomology of Shimura varieties, of which the modular curve is an example. So therefore, as a model where we expect the global Langlands correspondence to appear, we would be interested in studying the cohomology of Shimura varieties. So, and now the goal of this talk is therefore first to provide a link between these two sides. Namely, we want to put the study of Shimura varieties and their cohomologies into the geometric setup of Fargues Scholze. And it is in this procedure these so-called Igusa stacks come in, which are some newly constructed geometric objects that plays a very similar role as the Shimura varieties. And then after providing this link, I want to observe that already just linking these two sides will produce interesting information on the cohomology of Shimura varieties. And I want to talk about these applications. And then the second goal of this talk is, in the cases where we do have constructions of global Langlands correspondences in the cohomology of Shimura varieties, whether we can state or study some geometric form of local global compatibilities using these Igusa stacks. This will not have any complete answer, but I hope that I'll raise this question. Okay, so let's start by recalling the setup of Fargues Scholze. So here I will fix a rational prime P and consider a reductive group G over QP. And for simplicity of the following account, let's pretend that this group is split. And then Fargues Scholze can work with more general coefficient rings, but here we'll assume that it's torsion and probably just FL bar where L is not equal to P. And then we'll write G hat for the Langlands dual group of G considered as a split reductive group over lambda, and write W sub QP for the Wei group of QP. Then analogous to the global Langlands conjecture, the local Langlands conjecture aims to attach Galois representations to irreducible smooth representations of this p-adic group GQP on lambda models. And these local Langlands parameters will be continuous one cocycles from the Wei group into the dual group. So the dual group, in general, when the group G is not split, it has an action of the Wei group. Therefore, I talk about one cocycles. But here we assume G to be split, so one can ignore this action. And then in order to categorify both sides, and state a conjectural relation between the two sides on the level of categories or even derived level, one wants to replace these two categories by sheaves on certain geometric spaces. And inspired by the work of Drinfeld, Laforgue, etc. in the geometry Langlands, Fargues Scholze has choose to consider the stack of G-tossers on the so-called Fargues curve. So where in the geometric setting, they consider bone G for smooth projective curve. And then the representation side will be replaced by a suitable derived category of Étale lambda models. And later I will abbreviate this category by D bone G. And while on the L parameter side, the relevant geometric object is a stack of L parameters, which is constructed as a quotient by the moduli space of these continuous cocycles by the conjugation action of G hat. And so this will be a usual algebraic stack. While on the left-hand side, this will be a stack tested on perfectoid spaces with the so-called V topology. And then the relevant category of sheaves on this is some suitable bonded derived category of coherent sheaves with certain conditions. And their conjecture is that there will be an equivalence of categories between these two derived categories. So this conjecture is generally wide open, except for the tori case, which is settled by Conrad Zhou. But nevertheless, they're able to construct an action of perfect complexes on this stack on D bond G. So let's denote this action by star. And the existence of this action is a very compact form of encoding a lot of information. Now I'll give you two examples of these spectral actions, which will be relevant later. So the first example is the action of the structure sheaf on the stack of L parameters. So this action, the spectral action of this will be just the identity on D bond G. And as a consequence, if you look at the endomorphism ring of the structure sheaf, this maps to the endomorphism of this identity functor. And for any object in D bond G, we can evaluate it at this element to get a map to the endomorphism ring of this object. And let's assume that this element, this object A actually comes from an irreducible smooth representation. And then in particular, this endomorphism ring will be just one-dimensional over FL bar. Then, so this here is just a ring of global functions on the stack of L parameters. And it's also the same as its coarse moduli space. Then this composition gives us a maximal ideal here, or in other words, a geometric point on the coarse moduli space. So and because of its moduli interpretation, this is a semi-simple L parameter valued in G hat of lambda. So this is what we will call later the Fargues Scholze parameter attached to this irreducible representation. And the second example on the TEL is that if we start with an algebraic representation of G hat, a finite dimensional algebraic representation on lambda models, then we can consider, because our stack of L parameters is a quotient, we can consider the trivial bundle on this moduli space tensored with lambda and equipped it with a diagonal or anti-diagonal, depending on your convention, action of G hat. So this descends to a vector bundle, which I call curly V on the stack of L parameters. And we can look at its spectral action. And this will turn out to be acting via so-called Hecke correspondences. So namely, over G, we can consider a so-called Hecke stack, which is a stack of correspondences in the following sense. It parameterizes a degree 1 Cartier divisor, Clair's Cartier divisor, on the Fargues curve, together with a modification, meromorphic modification of two vector bundles, that is an isomorphism away from the divisor. Then from here, it has two projections to G by remembering the first or the second vector bundle. So and then on the stack, this Hecke stack, Fargues Scholze was able to prove a version of geometric sataka, and in particular, this algebraic representation of G hat will produce some perverse sheaf on this Hecke stack, which we call S sub V, which will serve as a kind of a kernel of a Fourier transform. Then the spectral action of this vector bundle V will turn out to be acting as this Hecke operator labeled by V, which is just a push forward of the pullback of an object and then tensored with this kernel. Okay, so these are all the operations we'll need from Fargues Scholze's machinery. And then the next thing I want to do is to relate this to Shimura varieties. Okay, so let's start here. Okay. Why? There is an involution on the Hecke stack, but constructed in the way you have said. But this is not doing nothing on the. Right, so the short answer is this is not symmetric, but there is an involution constructed as in the way you said. Right. So for now, I will fix a Shimura datum consisting of a reductive group over Q and some real symmetric space. And this will determine a minuscule cocharacter called the Hodge cocharacter. And let's fix a level subgroup of the away from p-adic points of G. And I'll write E, which is a finite extension of QP for the reflex field of the base change of mu to QP bar, where I have fixed secretly an isomorphism between QP bar and the complex numbers. And now our local group will just be the base change of this global group to QP. And then I want to consider a Schumra variety with infinite level at P by taking the limit of those finite level Schumra varieties with deeper and deeper level at P. And these will be base changed to E. Well, since I want to put it into the Fargues Scholze setup, I will test them on perfectoid spaces and consider them as sheaves on those. So therefore, I put a diamond to indicate this. And on this level, on this infinite level Schumra variety, there will be an action of the QP points of G. Okay, so now the slogan here is that this infinite level p-adic Schumra variety should be actually created by this Heck operator attached to mu from some simpler geometric object encoding global arithmetic information. So, which can be put in into a precise sense, which is a conjecture by Scholze, namely there should exist some stack, which I call the Igusa stack, for its relation to the classically studied Igusa varieties living over bound G, such that if we look at the Heck stack with a bounded variant, which where I declared that the modification of the vector bundle is bounded by this cocharacter mu, then if I restrict to an open substack of bound G corresponding to just the classifying stack for the automorphism group of the trivial vector bundle, which turns out to be GQP itself, then the limit of this diagram should recover this infinite level Schumra variety quotienting out GQP. And then, so just sometimes for, in order to remember the geometric Galois action, one can also do the projection not just to bound G, but also remembering the position of the degree 1 Katia divisor, and we projected diff 1. So over a geometric base, you can also think of this as the classifying stack for the wave group of E, just to, so that you can do this Cartesian diagram also with a Galois equivariantly. And this composition of this projection to diff 1 will remember the geometric wave group action on the Schumra variety. Okay. So, and then in the joint work, with Patrick, Paul, and Daniel, we have proven certain cases of this conjecture. This will come up hopefully soon. That's so. Conjecture holds for a good reduction locus. Of Hodge-type Shimura varieties. And also, so for L not equal to P and the torsion, L torsion coefficient ring, we can show that the Igusa stack we've constructed is L cohomologically smooth of L dimension 0, which is a direct consequence of the Cartesian diagram above, which means that it admits a dualizing complex. And we have computed that its dualizing complex is constant, concentrated in degree 0. And this actually comes as a corollary to a version of the diagram on the integral level that we have constructed. Right. Okay. So now that we have this result, I want to talk about how this result allows us to use the machinery of Fargues Scholze to deduce, oh my God, to deduce interesting information of the cohomology of Shimura varieties. So, right, let's write the setup again. And then we use D to denote the dimension of the Shimura variety. And mu and E will be as above. But for simplicity, you can pretend that E is just QP and G to be split. Otherwise, what I'm saying below is not 100% precise. And then I will write F lower shriek or lower star for the sheaf on bond G obtained by star or shriek push forward of the constant locus system from the Igusa stack. And so I forgot to give names to those arrows. So in the diagram above, I want to call this vertical map from B GQP to bond G I1. And this horizontal map from the infinite level Shimura variety Q. Okay. And then I will write R mu for the tilting representation of G hat labeled by mu. This is an analog of highest weight representation for mu, except that we're in the model setting now. And then this will determine some vector bundle on the stack of L parameters, as we have explained, and I denote it by curly mu. And the corresponding Heck operator will be labeled by T mu. So the first observation is that the cohomology of this infinite level Shimura variety, which I will just take the compact support one, but the usual cohomology is the same, is, so first of all, just RQ lower shriek of lambda, but then using proper base change along this diagram twice, you can rewrite it as the I1 pullback of the Heck operator T mu applied to this lower shriek with a shift and twist coming from this integral kernel. So this comes from the fact that in this case, SV mu will just be the constant sheaf with a degree shift and twist. And almost as tautology, this will be the same as I1 pullback of the spectral action of V mu on this sheaf. Here, let's call it F shriek tilde. Okay. So far, okay, nothing has happened, except that we have a new formula for the cohomology of Shimura varieties. Which first of all tells us that the information of this global sheaf if tilde shriek is rich enough to recover the cohomology of Shimura variety. And I want to make the remark that actually this information is strictly more than just the cohomology of the Shimura variety. This is because, for example, the underlying state of the underlying topological space of Bond-G is homeomorphic to the so-called Kotlitz set as a topological space, giving rise to a locally closed stratification on Bond-G called the Newton stratification. And this sheaf F, so the support filtration coming from the stratification of this sheaf gives rise to a spectral sequence on the cohomology, computing the cohomology of Shimura varieties. And if one worked a little bit harder to identify the graded pieces, then one will recover the what is classically known as the Mantelfans product formula. So which you can view as a zeros application. But next one I want to explain is that, again, purely by rewriting the cohomology of the Shimura variety in terms of the spectral action, one can deduce Eichler-Shimura relations almost for free. So as far as I understand, the idea of using spectral action to recover Eichler-Shimura relations can be dated back to Drinfeld and Lafogue, but the first application to Shimura varieties is probably due to Seldru, and there is the work of Zhio Wu and Koshikawa on this. So, okay, so I should also say that everything here I say is based on the joint work with Patrick, Paul van Hopten, and Daniel. So the observation is the following. So we have this curly V mu on the stack of L parameters. And we can look at its endomorphisms. And this maps to the endomorphisms of any object in the essential image of the spectral action of this thing on Bond-G. So in particular, the cohomology of the Shimura variety. And also as a sheaf on this classifying stack, in particular, it remembers the QP representation as well as the Galois. And then here, because this is a so stack of L parameters. We have on the moduli space of L parameters a universal L parameter, and this goes from the Y group to G hat, and then we can both compose it with this representation R mu to get an action of the Y group as automorphisms of this vector bundle, but it's well defined only up to G hat conjugation. But nevertheless, we can take the characteristic polynomial of this element, this thing. So So we can write down this polynomial, just the alternating sum of -1 to the I of the trace of this universal, or this endomorphism on wedge powers of this vector bundle. And then x to the I. Note that these traces, these are G hat invariant, and in particular, they descends to a global function on the stack of our parameters. And this polynomial can be viewed as an element in this polynomial ring with one variable here. And then, so it follows from Hamilton-Cayley's theorem that this polynomial annihilates the action gamma. And now, if you choose gamma specifically to be a lift of the Frobenius and then pass to hyperspecial level, so we're here, FQ is the residue field of E. So we'll get a well-defined ring map from just the global functions on, so it turns out a substack of the stack of L parameters where the universal L parameter is unramified. So joined with one variable and quotienting out the image of this polynomial inside here, where here it will not depend on the choice of the Frobenius anymore because there is a not ambiguous because the universal L parameter factors through the image of the Y group inside the absolute Gaussian group of the residual field, and this maps to the endomorphism of the cohomology of the Schnorr variety at hyperspecial level as a module over the spherical Hecke algebra. And another observation is that here, actually, this ring of global functions on this unramified substack is also identified with the spherical Hecke algebra. And then you can further identify this polynomial with the usual Hecke polynomial, and this recovers the usual statement of Eichler-Schunroth relation. And the remark to make here is that this can already be done at Euler-Horrich level, because this is the place where the universal L parameter will actually factors through the tame quotient of the Weil group, while any topological generator of the tame inertia will act unipotently. In particular, their characteristic polynomial is known. Okay, so how much time do I have left? Not many time. Okay, so I'll just mention briefly another application we can do is to prove torsion vanishing. This is after the work of Caraiani Scholze and Hoshikawa, Mafalda Santos, Ana and Lee. Due to time constraint, I will probably skip this part, but just say that we have torsion vanishing results for the generic part of the cohomology a better statement is that the generic part of cohomology of compact Hodge-type Schnorr varieties are concentrated in the middle degree. So here we are following basically the strategy of Hamann and Lee, but by producing this global sheaf F lower Schritt tilde, and together with rewriting the cohomology of the Schnorr variety, as well as proving perversity of this sheaf before shifting and twisting, we make the argument for this torsion vanishing almost purely formal. Okay. Okay, so in the last couple of minutes, we will go back to the question about local global compatibility. So here, as we have explained, we have now this Igusa stack living over G, and we have a sheaf. So either using the Schritt push forward or the start push forward on G, controlling the cohomology of the Schnorr variety, then the question to ask is whether we can use this instead of the cohomology of Schnorr varieties to construct global Galois representations and talk about compatibilities. So more precisely, if we fix a finite set of primes containing L and P, and as well as all the places where this K upper P is not hyperspecial, then this sheaf is actually equipped with an action of a global Hacker algebra, unramified Hacker algebra, which is the product over all places not in S of the spherical Hacker algebras at these places. And then if we fix a maximal ideal here, then we expect the following to happen. So first of all, if this maximal ideal, in other words, Hacker eigensystems, appear in the support of either this lower trig or lower star, then there should exist a Langlands parameter, global Langlands parameter, going from the absolute Galois group of Q to the C group of G with values in the residue field of this maximal ideal, and then we take an algebraic closure. And this construction of Galois representation should be unramified outside S and matching Frobenius eigenvalues with Sataka parameters. And then, so a version of compatibility with the local Langlands correspondence by Fargues Scholze is that if we now look at the restriction of this Galois representation to the wave group at a place P, and then take its semi-simplification, then in particular, we can look at this sheaf first localized at this global maximal ideal, and then further localize this at the semi-simple L parameter using the spectral action of Fargues Scholze. Then we predict that this should be just the same of this sheaf localized at this global maximal ideal, which means that this global away from P Hacker eigensystem actually determines this local parameter at P. And this is a version of compatibility. And then similarly for lower shrink. And then if we, so inspired by the Kottwitz conjecture, if we put suitable conditions on M, so for example, this is non-Eisenstein, meaning that the Galois representation attached in one is absolutely irreducible, then we expect that this localization should agree with the conjectural Hecke eigensheet for this local parameter. Up to an explicit multiplicity. And then in the end, there's some geometric result, expectation is that we expect that both lower Schrick and lower star, these global sheaves, will be perverse with respect to the perverse T structure on bond G given by the Newton stratification, concentrated in different ranges. And further, if the maximal ideal is non-Eisenstein, then the localization of these two sheaves should actually agree. And both of them will be perverse. Okay, so these are general expectations. And then I'll finish by stating what we can prove towards these expectations. So this is basically okay. So basically, if we restrict to the setup of Caraiani Scholze, so we're just to briefly recall, they start with an imaginary CM field whose totally real subfield is not the rational numbers, and then consider some Hermitian space of dimension 2n over f. And this determines a PL datum of type A and attaches a Schmurr variety where the relevant group is a quasi-split unitary similitude group. Then in this case, so the expectation 1, 2, and 4 holds. And 3 holds if this local parameter is generic in a sense of harmony. And now just one more remark is that originally Caraiani and Scholze has to assume the totally real subfield is not Q in order to construct this global Galois representation. But then Ana has explained to me a nice trick using congruences developed by Vincent and Shin, where this assumption can be removed. Okay, I guess I will stop here.
Any questions?
So when you say the setup, this is like for unitary stuff like this, right? Setup Caraiani Scholze 19. Okay, but the result.
Okay, I should also say that most of the results are based on the original strategy.
your Igusa stack. I think your Igusa stack was what type A and C, if I remember correctly.
And there's no values.
So this is also for type C.
The problem is, so the construction of the Galois representation uses, so first move to characteristic 0, and then uses the null construction of Galois representations in GLN. And then, but there are some constructions for, yeah. I mean, so therefore this result doesn't naively apply in the C case. But I know that there are some constructions for Galois representations to the private machine for symplectic groups of
Any other questions? Thank Mingjia again.